prog3.s introduces a host of new concepts in building on the prior segment's discussion of LDR and STR. It performs an assignment that in C would read val A equals 143 minus 8i 2097 minus val B plus negative 200. That mouthful is repeated up there on screen. There's no real point to the assignment as far as its logic goes. It's just a good assignment with which to demonstrate a lot of interesting concepts. So that's the one we'll be doing. Now, in particular, we'll be setting up val A and val B as variables, and also the string 2097 as a variable, and then working with them. Now, let's start with lines 2 through 10 of the prog3.c, ignoring for the moment the .text assembly directive on line 1. So far, our assembly code has described assembly instructions with some labels. But programs also have data, and every assembly language includes directives that describe memory areas containing data. These can be intermingled with assembly instructions, and the result is a machine language translation that has code and also has data areas, often with pre-filled values when the program starts. Some data directives describe just the size of the data area, leaving the area uninitialized, but more of them describe both a data area and its initial contents. The initial contents become part of the assembled executable, and they're loaded as part of the program when it starts. There are 3 pieces of memory data that our assignment statement needs. 2 are the variables val A and val B, and then the third is the string 2097, and val B has to be initialized to 2257. Let's start with the val B variable. On line 3, labeled as val B, is a word directive. This reserves a word or 4 bytes of memory containing the integer value indicated, 2257. Next, we add the string 2097. The ASCII directive on line 6 describes a quote delimited sequence or string of 5 bytes of memory containing ASCII codes. A 2 for the 2 is byte 54, ASCII code 54. The 0 then has a byte containing ASCII code 48. The 9 gives us a byte containing 57, and the 7 a byte containing 55. The 5th byte for ASCII code 0 is represented by the /0. ASCII code 0 represents no useful symbol. It's usually used as a marker for the end of string. And a C compiler automatically adds it to the end of any string like 2097, by the way. To be clear, the \0 comprises or represents 1 ASCII code. I'll represent these here in the diagram with a 4-byte long box containing 2057 and a 5-byte long box containing those 5 ASCII codes, 1 byte each. And a quick reality check in lecture question: why do we need a \0 escape code to represent the single ASCII code of 0? Why not simply write 20970? And the answer there is that that would end the string with the ASCII code for the symbol 0, which is actually code 48. If we write 0 alone, what we mean is ASCII code 48. The \0 means literally ASCII code 0. Now, the .word directive on line 10 reserves a word at the label numsterlog, but instead of a direct number, it has the value numster. Numster is the address of the ASCII string here at line 6. Labels like numster represent memory addresses, and they can be used like integer constants in some contexts, including as the value of a word directive. The word reserved at line 10 is thus an indirect address. We saw registers that contained addresses in the prior segment. Here we have a memory location that contains the address of another location. We'll draw that with a pointer in the diagram. And another in-lecture question. The pointer is a nice abstraction, but there's an actual address involved here, so assuming the entire program starts at address 0, then what value would actually be at location numsterlog? What address exactly does numster represent? After thinking about it a bit, there is just one data word before numster, and that's the val b. So numster represents address 4, which will be the content at numster of numster loc. So let's fill that in there. And just to be clear, note that labels themselves don't take up space in the memory. They're just names for memory addresses. Only instructions and data directives occupy space. And that brings us to question 3. Assuming that the string at numster starts at an address that is divisible by 4, we've just agreed that it would start at address 4, what is wrong with the word at numster loc following immediately after it in memory? Consult earlier lectures on machine language fundamentals if you need to. The thing we're getting at here is that in earlier lecture we talked about how 4-byte quantity is needed to start at divisible by 4 addresses in order to work with a 32-bit memory bus that loads memory 4 bytes at a time. If the word starts right after, if the numster loc word starts right after the 5-byte 2097/0 string, it won't begin at such an address. The align to directive on line 7 solves the bus alignment problem that we just discussed. It tells the assembler to move the next data item, the dot word numster, so that it starts in an address divisible by 4. This means that there will be 3 unused bytes after the end of the 2097. So I'll expand this diagram here to show 3 more bytes of space and make it a full 8 bytes long. The 2 in the align to directive would suggest a divisible by 2 address, but it's misleading. There are cases where one might want to align by different rules, e.g. by addresses divisible by 2 or even 8, but alignment is always by some power of 2. You would align by 2 or 4 or 8. No one tries to align at a divisible by 3 address, for instance. So, for better or worse, the argument to align is a power of 2. In other words, dot align to means to align at an address divisible by 2 to the second power, or 4. A question there, just to be sure we got that straight. What assembly directive then would ensure the next data item aligns at an address divisible by 8? And the answer here is that would be a dot align 3, since 2 to the third power is 8. And then finally we come to val A, which in fact is defined way down on line 48 as another word, this time with a default value of 0. This is just another variable, but it is in a different area from the other data. We'll come back to that later. Now, let's look at the code for prog3.s as opposed to the data. The code starting up on line 15. The first line here, LdrR0 val b, loads the value 2257 at val b into R0. But this doesn't follow the LDR form discussed in the prior segment. For one thing, there's no address register, and it looks as though a direct address, represented by val b, is part of the instruction, when we made a big point about how the LDR has no room for a full address, allowing at most a smallish address offset relative to the address register. This line is a pseudo instruction. It's an assembler shorthand that stands for a more complex and less readable real instruction. And as the comment itself indicates, what line 15 really means is load R0 PC relative to the PC, that is, minus 16 bytes. Recall from the prior segment that LDR may use the PC as an address register, including offsetting from it. Thus, the real instruction offsets minus 16 bytes from its own PC location to arrive at val b, from which it loads 2257. And that leads us to question number 5. Why exactly do we need an offset of minus 16 from the current PC? What 16 bytes are we backing over, and what's in them? If you think about it, the answer is that we need to back over the LdrStr loc word plus the 8 bytes for the 2097 string, and then that's of course including the 3 bytes of padding, by the way, generated by the align2, and then finally the 4 bytes of val_b itself to get to the starting address of that word. And then another little question here, why not just write move R0 2257 and use a simple move? We've used move instructions to load constants into registers in earlier examples. The answer there, recall from earlier segments that the move instruction allows only a limited range of constant values. Values above 255 are not guaranteed to work with a move, but a word in memory can contain any value we like. So if you want a truly arbitrary constant, you need to arrange a memory word that contains it and then load it in this fashion. So then, summarizing, you may write the pseudo instruction LDR some register RX, comma, and some label to load the memory word at some label into RX, and the assembler will translate this into the real LDR instruction, which is going to be LDR RX and then PC and some correct offset to get the desired value. This works for any label as long as it's not more than 2048 bytes before or after the instruction in question, since, as you may recall, that's the limit of LDR's memory offset. So with that in mind, question 7, take this LDR instruction down here on line 20 and rewrite it as a PC relative load with the correct offset. Remember that instructions are each 4 bytes. So thinking about that, we have to back up across 4, 1, 2, 3, sorry, across, yes, 4, 1, line 19, line 17, 16, and 15, 4 instructions. And then we also have to back up across the LdrStr loc labeled word itself. So that's 5 words, or 20 bytes. Thus, LDR R1, comma, PC, comma, minus 20, pound minus 20, or LDR R1 R15 if you want to use that instead for the PC. Either will work. An offset of -20. Okay, so let's move on to the next instruction, which is somewhat simpler. This is a move n, or move negated. You can't put even a small negative value into a register using move, since it only allows positive constants. Instead, use MVN, which is just like move, but it negates the value being copied into the target register, whether it's a constant or the value of another register. However, for reasons that will be clear when we discuss 2's complement notation in the next module, there is a kind of oddity here. MVN produces a number 1 lower or less than would be expected. So for instance, where we might expect minus 199 as the value in R1 after line 16, we'll get minus 200. There's more on that later. Just take it on faith for now and make that one value adjustment when you use MVN. Adding the 2257 in R0 to the minus 200 in R1 on line 17, we get R0 holding 2257 minus 200, or 2057, for the first step in computing our target expression over here. And that should be enough for this lecture segment. In the next segment, we'll look at the loop on lines 19 through 34, which converts 2097 \0, the string, to integer 2097, and introduces a bunch of new ideas along the way.